Okay, so we've done first order equations. We'll look at second order equations. We'll start with sort of the easiest case, which is homogeneous second order linear constant coefficient equations with real eigenvalues, which is kind of a mouthful. We'll have to define what all that means. We'll say why it's important. Linearity, very important. Finding solutions, 2 real eigenvalues, 1 repeated eigenvalue. So a second order linear constant coefficient ordinary differential equation has this form, right? So A times a second derivative plus B times the first derivative plus CY. Second order because it's the second derivative. Linear because Y, they're not multiplied to each other. They're not inside of a sign or an exponential or anything goofy. They occur to the first power, not multiplied by each other. And it's constant coefficients because A, B, and C, these things are constants. Homogeneous has this thing, which is often called the forcing term, equal to 0. And so we're focusing on homogeneous equations, and we'll move on to non-homogeneous equations next week. So importance, why are these things important? F equals ma. A is the second derivative of position. So if we're talking about how the physical world works, right, we use second order equations because that's what F equals ma is. A couple common forces that you'll see is friction, E times V. V is dy dt is velocity, and the spring force, which is ky. It's usually minus ky, I think. And this is minus bv. So we want the force of friction to be in the opposite direction from velocity. We want the spring force to be opposite direction in the extension of the spring. So if we actually start with F equals ma, that's mass is d squared y dt squared. So that's going to be for mass on a spring, that will be equal to minus b dy dt minus k dy dt. So force is the force of friction, the force of the spring, plus whatever forcing function you're applying. And so that means that second order linear constant coefficient equations are what mass and the springs look like. If you think about any kind of object at equilibrium, they tend to behave like a mass on a spring. So if a bridge is hit by a gust of wind, it oscillates a little bit, and then oscillations die down because of friction, the friction force, right? That's the minus by dt. So you can model the motion of the bridge by this kind of an equation. And you'll see also in electrical circuit theory, L dx squared I dt squared, well, this equation, L is inductance, R is resistance, C is capacitance, and I is current, and we'll see these equations in a little bit. So linearity. So here's our second order homogeneous constant coefficient thing. So suppose we have two solutions. Show that a linear combination of those two is also a solution. So how do we prove this? Well, y1 is a solution. And you only get to be a solution means that if you plug it into the equation, you get 0, right? This holds true because y1 is a solution. Likewise, y2 is a solution. What does that mean? That means that a second derivative of y2, whatever function it might be, plus b first derivative of y2 plus c y2 equals 0. Great. We want to show that the new function that we get by multiplying the first function by m and the second function by n, I don't know why I'm putting in parentheses all the time, n y2 of t is a solution. So how do you check if something is a solution? You plug it in and see if it works. So left-hand side, a times second derivative, d squared dt squared of my function. So we'll plug that in, my1 plus ny2 plus b times the first derivative of my function, my1 plus ny2, plus c times my1 plus ny2. So that's my left-hand side with everything plugged in. If I grind away at this a little bit, what do I get? Well, I know that differentiating, I can bring constants out of different derivatives. And I know that I can break up derivatives just by differentiating this part and then take the sum with the derivative of this part. So what do we get there? We get a times m times the second derivative of y1 plus a times m times the second derivative of y2. And that should be a times n, because that's an n, plus b times m times the first derivative of y1 plus b times n times the second derivative of the first derivative of y2 plus c times m times y1 plus c times n times y2. So gather everything in terms of m. So we want all the terms with m's. So I have m times a d squared y1 dt squared. That's this term. And I have another m term here plus b m dy1 dt. And then I have another m term out here. Oops, I factored out the m plus cy1. So that's my three m terms gathered together. And then I'll get three n terms. That's this one. A d squared y2 dt squared plus b dy2 dt plus cy2. That's my third one. Yay, so what's all that equal to? Well, this stuff inside this parentheses, that's all equal to 0 because y1 is a solution. The stuff inside the parentheses here, that's all equal to 0 because y2 is a solution. So this becomes m times 0 plus n times 0, which equals 0, which is the right-hand side. So we wanted to show that this is a solution. That means when we plugged it into the left-hand side, it should reduce down to 0, which is the right-hand side, and it did, so it is a solution. Really useful fact. So how do we find solutions to this kind of a function? So we know when we solve y prime plus ry equals 0, you get an exponential. So what we're going to do is we're going to try and plug in y equals e to the rt into our second order homogeneous equation, see what values of r give us solutions. So if this is a solution to this, what does r have to be? So if it's a solution, what has to be true? Then a times the second derivative with respect to t of e to the rt plus b times the first derivative of e to the rt plus c e to the rt has to equal 0, right? If you're a solution, you get plugged into the equation, then you have to satisfy the equation. But we know how to differentiate this. Differentiating e to the rt twice just means pulling down the r twice. br e to the rt plus c e to the rt. We know e to the rt is never 0, so we can divide through by e to the rt, and what do we get? Well, we get a quadratic equation. So what is r equal to? Negative b plus or minus the square root of b squared minus 4ac all over 2a. So that's what r has to be. And there's two r's. Right, which is convenient. So if y equals e to the rt is a solution, then what does r have to be? R has to be one of the roots of the quadratic equation you get when you place the y squared, the second derivative with r squared, the first derivative with r, and the number with just a constant 1. So this is called the characteristic equation of the differential equation, and the roots of the characteristic equation are called the eigenvalues of the equation. And we know because we've done lots of stuff with quadratic equations, there's 3 possibilities: 2 distinct real roots, 1 repeated real root, 2 complex conjugate roots. So we're going to look at these 2 cases here first, and then we'll go to complex conjugates next. This process is going to get all the solutions to the homogeneous equation, and once we get the necessary linear algebra tools, we can say why that is. So what are all the solutions to this differential equation? So the characteristic equation is r squared plus 5r plus 6 equals 0. I can actually factor that. And I find my 2 eigenvalues. And each eigenvalue corresponds to a particular solution. And the general solution is a combination of those 2. K1 and K2 are constants. And you can grind through that and show that that's actually a solution to this. I'm also claiming that that's all the possible solutions to that differential equation are given by this formula, right? That's why it's called the general solution. We have to wait again on a little bit of linear algebra to be able to justify that statement, but we're getting to that point soon. So the general solution is that. So what do solutions look like? Here's t, here's y, and we want to plot solutions to this. Note that there's no slope field or anything for this because it's a second order equation, not a first order equation. So e to the minus 3t looks like that. E to the minus 2t looks like that. So signs are both negative. So any combination of these things is all going to have the same properties. They're all going to look more or less like these curves. So all solutions go to 0 as t goes to infinity. Right? They all have this asymptote here. And they go to infinity, plus or minus infinity, as t goes to minus infinity. All except for the case where k1 equals 0 and k2 equals 0, right? And then the solution is just y equals 0 as the solution. So negative eigenvalues means that you go to 0 in forward time and you come from positive infinity. So here's a initial value problem. What does the solution of this look like? Well, we found the general solution to this above. We just have to match the initial conditions. And note the initial conditions are on y, and we have another initial condition on y prime. There's a reason why there's 2 initial conditions here. It has to do with the fact that there's a second order differential equation. And again, once we get a little bit further into linear algebra, we can explain exactly why we need 2 initial conditions. So, but we're going to need to know what the derivative is. So there's the derivative of that. So one initial condition is y of 0 equals 4. And that becomes 4. We plug that in for y. If we plug in 0 into t, this becomes 1. And we plug 0 in for t there, that also becomes 1. So k1 plus k2. Y prime of 0 equals minus 1. So replace this with a minus 1. Put a t equals 0 in here. That'll give me a minus 2k1 and a minus 3k2 because the exponential terms become 0. And great, we know how to solve these things now that we've done a little linear algebra. We'll say multiply the top one by 2, 2k1 plus 2k2 minus 1 equals minus 2k1 minus 3k2. If I add them together, I get 7 equals minus k2. So k2 equals minus 7. K1 equals, well, if K2 is minus 7, K1 has to be 11 from this equation. Great. So our, I don't know where I'm going to put my sketch, but our solution to this initial value problem is 11 e to the minus 2t plus, minus 7 e to the minus 3t. And what's that graph going to look like? Well, e to the minus 3t, 3 is bigger than 2. So as we go out to minus infinity, this term will dominate. So it'll be actually negative down here. And as we go to infinity, positive infinity, both of these go to 0. So a graph should look something like that. But it'll be defined for all time. So here's another one. Find all solutions to the following differential equation. D squared y dt squared minus 5 dy dt minus 14y equals 0. So how do we solve this? Characteristic equation is r squared minus 5r minus 14 equals 0. And I can factor that. Let's see, minus 7 times r plus 2 equals 0. So r equals 7, r equals minus 2. Our two solutions that come from our eigenvalues are e to the minus 7t and e to the minus 2t. So a general solution is y equals k1 y1 plus k2 y2, or since we know what y1 is, k1 e to the minus 7t plus k2 e to the minus 2t, except it's a plus 7. So note that we actually have two separate solutions. E to the 7t looks like that. So positive eigenvalue means you're going to infinity in forward time. Let me rewrite that. Eigenvalue is positive. So we go to infinity in forward time. E to the minus 2t, on the other hand, is the negative eigenvalue. And we go to 0 in forward time. Right? So positive means you're going up to infinity in forward time as t goes to infinity. Negative means you go to 0 in forward time, and vice versa for backwards time. So here's another initial value problem. We found the general solution above. Y of t equals k1. Oh, this is supposed to be a 5. K1 e to the 7t plus k2 e to the minus 2t. Again, we have initial condition and initial condition on the derivative, so we need the derivative. 7k1 e to the 7t minus 2k2 e to the minus 2t. And so our condition is y of 0 equals 1. That means we want to place this with a 1. K1 plus K2, because if you replace t's with zeros, the exponentials become equal to 1. And y prime of 0 equals to minus 3. That gives me minus 3 for y prime of t equals 7k minus 2k2. And we can solve that, multiply the top by 2, leave the bottom alone, and add Minus 3 plus 2 is minus 1. 7 plus 2 is 9, and then these cancel out. So K1 equals minus 1/9. And if K1 plus K2 equals 1, then that means K2 has to be 10/9. So Y equals minus 1/9 e to the 7t plus 10/9 e to the minus 2t. So if we look at graphing this, e to the 7t. We look at graphing this, 10/9 e to the minus 2t will look something like this. A negative exponential. Minus 1/9 e to the 7t will look something like that, because it's a minus 1/9 e to the 7t, so it's flipped over the x-axis. So what's our solution going to look like? Our solution curve will actually, what was my y0 anyway? 1. We'll start up here along this, and then it will transfer here down to this one that's going down to minus infinity. So that's our solution curve. This is close to 0, so if you add something close to 0 with some really big number, you get something really close to this graph. This graph is really close to 0, so if we're adding this graph and this graph together, if this one's really close to 0, we end up close to that. So the solution curve actually transfers from one to the other as t goes forward in time. So the last case is, what about one repeated eigenvalue? Same procedure for solving these things. Characteristic equation, r squared plus 4r plus 4 equals 0. You can factor that. It actually becomes r plus 2 squared equals 0, which just means r equals minus 2. So y1 of t equals e to the minus 2t. I need a second function. And again, that's once we get to the linear algebra parts, we'll be able to explain why that is. And we'll be able to explain why we multiply the first one by t to get the second one. So to verify that these things are solutions, we just have to differentiate them. So is y1 a solution? Question mark. Well, you plug it in and see if it works. So d squared dt squared of e to the minus 2t plus 4 d by dt of e to the minus 2t plus 4 e to the minus 2t equals what? Well, this is plugging e to the minus 2t into the left-hand side. We would hope that we would get the right-hand side at some point. So if we differentiate this twice, we pull out a minus 2 and then another minus 2 here. So that's actually going to be a 4 e to the minus 2t. If we differentiate once here, we'll pull out the minus 2 multiplied by the 8. We get a minus 8 e to the minus 2t. And then there's nothing to differentiate. And that equals 0. Yay, so there's our solution. What about y2? Well, left-hand side, d squared dt squared of t e to the minus 2t plus 4 d by dt of t e to the minus 2t plus 4 t e to the minus 2t. So we're checking if this is a solution by plugging into the left-hand side and seeing what we get. So what is this going to be equal to? We'll write this down on the next line. This is still the 4t e to the minus 2t. Differentiating this means differentiating the first times the second plus the second, derivative of the first times the second plus the first times the derivative of the second. So the derivative of this is going to be e to the minus 2t, because we differentiate the t, and multiply by e to the minus 2t, and then plus t times minus 2 e to the minus 2t. That's the derivative of this part. And all that is times 4. So second derivative of t e to the minus 2t is going to be the derivative of the first derivative. So this part, the second derivative, is going to be the derivative of what we have here. So if we differentiate this, we get this term just has a minus 2 e to the minus 2t. Differentiating this term, or we differentiate, it's a product again, so we differentiate the t, and that leaves us with a minus 2 e to the minus 2t. And then we differentiate the minus 2 e to the minus 2t, but leave the t alone. So pull down another minus 2, and that gives you a 4t e to the minus 2t. So there's our second derivative. So what does all that equal to? Well, in here, we've got a minus 4 e to the minus 2t plus 4t e to the minus 2t plus 4 e to the minus 2t plus 4, minus 8. Ooh, did I lose a t e to the minus 2t? I did not. That should have a t in it. Minus 8 t e to the minus 2t. That was the 4 times the minus 2. That gives me the minus 8 plus 4t e to the minus 2t. So what have I got here? This and this is 8t e to the minus 2t. That cancels out this. 4 e to the minus 2t and minus 4 e to the minus 2t cancels out that. So we've got our two solutions. And now we can do the same thing that we did before. What do these things actually look like? If we graph this, e to the minus 2t looks like that. We've seen exponentials. T e to the minus 2t, keep in mind that if t is negative, right, this whole thing is negative. And if t is positive, the whole thing is positive, because this is a negative, this is positive. The t changes sign. So when t equals 0, y2 is equal to 0. But when t is negative, y2 is also negative. And the e to the minus 2t makes it really big. But the e to the minus 2t is going to drive it all down to 0. So this is what the second function looks like. I have to be a little bit careful about how these things combine. So for a repeated eigenvalue, to solve this, we know what the general solution is. Is y of t equals k1 e to the minus 2t plus k2 t e to the minus 2t. Tells me that my derivative is minus 2 k1 e to the minus 2t plus k2 e to the minus 2t plus minus 2 k2 t e to the minus 2t. Remember, you have to use the product rule to differentiate this. That's why we got these two terms. So using our initial conditions, y of 0 equals 1. That gives me 1. We plug that in here, equals k1, and plugging t equals 0 makes this equal to 1. Plugging t equals 0 just kills this term off entirely, right? So that term just goes away. Y prime of 0 equals 1. That tells me that 1 equals minus 2k1 plus k2. And then setting t equal to 0 cancels that out. So that's what we have. So k1 equals 1. What does that tell us about k2? 1 equals minus 2 plus k2, or k2 equals 3. So the solution of this is going to be y equals e to the minus 2t plus 3t e to the minus 2t, which is 1 plus 3t times e to the minus 2t. And so when t is actually less than minus 1/3, this whole thing, this line becomes negative, right? This is a line, 1 plus 3t, and it changes sign. So as t goes to infinity, this dominates. So that means that we're actually going to be approaching 0. As t goes to minus infinity, this is negative, and this gets very, very big. So we end up with a function that looks like that. And there's our solution to this equation. So that gives us a solution to way back up here. Here we go. So find the characteristic equation, find those roots. The two solutions are going to be y1 equals e to the r1t, y2 equals e to the r2t, and the general solution is k1 y1 plus k2 y2. If you have a repeated root, then y1 equals, oh, we'll do this down here, y1 equals e to the rt, y2 equals t e to the rt, and the general solution is, as always, this. Now, one question is, what happens when you have complex roots?